minus by 7.741 times 10 to the power 9 y squared. Now, why did we use this one? Okay, and we did not use this expression over here, because we want to find the higher value at point A, not the lower value. Okay, why the higher value is the previous, or the equation on the next page, is because of the thickness. Down here, the thickness is 0.16, whereas over here, the thickness is twice of 0.02. So you take the one with the lower thickness. So lower thickness, higher stresses. Okay. So this is 32.707 times 10 to the power 6 minus 7.741 times 10 to the power 6, and the y bar will be equal to 0.015 squared. So the stress at point A, or down here, I should say the shear stress at point A now is equal to 32.7 or 7.741 power 6 times 0.015 times 0.015, and then 32.707 power 6 minus by. So it's equal to 32.7005 times 10 to the power 6. Okay. Now, maybe I did, no, I think I did something wrong. This is to the power 9. I do apologize. That's why it looks a bit weird. So this value is wrong. 7.741 power 9 times 0.015 squared. Then you have 32.707 power 6 minus by, the answer is equal to 30.965 times 10 to the power 6 Pascal. Okay. And then we are going to look at the shear xy at point B. And shear xy at point B, if we look at point B, y is equal to what? Y is equal to 0.03 meters. Okay, you can use the same equation, right? Because both equations, whether you take from the top, okay, we shall circle now, this is from the top, all right? And from the bottom is the same, because our first moment of area is the same. Okay, so you can use the same equation. So now shear xy at point B is equal to 32.707 times 10 to the power 6 minus by 7.741 times 10 to the power 9, and we change this to 0.03, and we square. Okay, so 7.741 power 9 times 0.03 squared, 32.707 power 6 minus by, so it's 25.74. Okay, 25.74 times 10 to the power 6 Pascal. So if we are going to sketch how this profile or the shear stress will look like, I will do that now. Okay, so we're going to sketch. Okay, so we know that if this is our geometric centroid, right, and this will be our one of our axis. Then we have another axis running horizontally. Right, so this is our shear stress, xy. This is our y, this is our 0. And if we were to draw our boundaries, so again, this is just a sketch. We know over here, this is 0.035. Over here, this is 0.015. Over here, this is minus 0.065. So this is how it will look like, okay? So down here will be 0, reach to the top. Because of the piecewise equation, the thickness changes, okay? And then this just does this. And this over here, this will be our tau max, okay? This over here, this value, we do know, okay? That value is equal to what? That value is equal to 30.965. And there's another value that we know also, and is this value over here. Okay? And this value over there at this point is equal to 25.74 times 10 to the power 6 Pascal. So in the term test, if I ask you to sketch, you have to sketch this. Okay. Now, so this is one unique problem, right? And it happened. So if to conclude on this example, it happened that tau max occurs at the what? At the centroid. Okay, for this case. Okay. Now, if we were to go back on the theory again, okay, so we know that the shear stress is equal to V over I Q over what? Over T. Okay. So we are aware that this is a what? This is a constant. Okay. And we know tau max will occur in two possible situations. Okay. And it is dependent on the Q over T, okay, not theta, sorry, is dependent on the Q over T ratio. Okay. So we know tau max can occur when what? When we have what? Tau max can occur in one situation where you have Q max divided by what? T mean, right? Maximum first moment of area, minimum what? Thickness, right? But we also cannot forget the situation tau max can also occur when we have Q divided by T mean. Okay, so Q does not need to be what? At its maximum. Okay, but it can also cannot be the smallest. It cannot be a Q mean, but it can be a what? A specific Q value. Okay, so this section over here we're going to talk about is we are going to highlight the importance of the what? The importance of Q over T ratio. Okay, why I emphasize on that, because a lot of times we always assume that the centroid will always have the what? Maximum shear stress, and this is not true at all. Okay, I repeat, this is not true at all. Okay, now let's look at a problem regarding the Q over T ratio. Okay, so it's the next problem that we're going to look at, this problem over here. This problem was a term test question that I gave, okay, and it has optimization in this question. Okay, let's look at this question. So this is example number 2. Is the importance of the Q over T ratio that I want to highlight, okay? So about this problem, we have a beam having a cross-section shown, okay? So we have a cross-section, determine the largest value of P, such that the shearing stress is not to exceed, I'll write out, so it's not a value, I apologize. So this is equal to 130 times 10 to the power 6 Pascal, okay? So the first part is straightforward. Is the second part. The second part is the part that is you need a bit of thinking. The wall thickness of the beam such that the shearing stress, the maximum shear stress at the centroid, and the region with the smallest wall thickness are equal. Okay, the outer perimeter of the beam must remain what? Constant. So you cannot change the outer perimeter. Outer perimeter means this outside cannot change at all. Okay, this has to be fixed. Okay, you only can change the thickness, and the thickness, okay, which I will highlight, is this thickness over here. And the distance, okay, between the beam, okay, this is 590 millimeters, and the other one is at 550 millimeters. Okay. So let's see what is the problem with this question. Okay. Okay. So again, what we want to highlight is the Q over T ratio. Okay. So we are going to look at 2 points now. Okay. So this is the cross section we have to look at. And based on observation, right? Based on observation, we are aware that this is the centroid. And we are aware. So I'm going to break down the problem, okay, in this way, okay. So this is where a lot of analysis occur, okay. So I'm going to pick this point as point A. Over here is point B, and over here is point C, right? And I'm going to sketch the shear flow is going in this direction. Okay, so the shear flow is going in this direction. Okay, and this is how the shear flow will flow. So the rule says that the thickness is perpendicular to the shear flow. So we know that this is the thickness that will change. Okay, or this also is the thickness, but this thickness cannot be changed because the perimeter has to remain what? Constant. Okay, so we look at points, right? We have A, B, C. Okay, if you look at the Q, okay, so if I will have our transformation, this is the Y, this is our Z. If we look at QZ, right, point A will have the minimum QZ. Point C will have the maximum QZ. Okay, right? Point B is just somewhere in between. If you look at the thickness, right? If you look at the thickness over here, down here is equal, the thickness is equal to what? 0.04. Oh no, 0.05. At point C is also equal to what? No, point A, sorry. Point A can be, not can be, point A itself is equal to 0.02. Point C is equal to 0.05, right? And point B is also equal to 0.02. So there are 2 points of concern now, okay? Point A is impossible because QZ is at its what? Minimum. Point B is somewhere in between what? Q max and Q min. And regarding this point, it is equal to what? 0.02, right? So we have to check on this point over here, point B,